Good morning, students. In the previous lecture, we studied how we can go from time domain to frequency domain using Fourier transform. So the Fourier transform of the signal xt is x j omega. It's equal to from minus infinity to infinity x of t e to the power of j omega t dt. And we saw how we go from frequency to time domain by using the inverse Fourier transform. Today in this lecture we see some of the properties of continuous time Fourier transform, such as linearity, time shift, convolution, and multiplication properties. For example, here, first one is linearity property. If I have a signal which is a sum of two signals, ax of t plus byt, this is straightforward. The Fourier transform is a times x j omega plus by j omega. Okay, if the Fourier transform of x of t is x j omega, what is the Fourier transform of x of t minus t naught? That means if I shift the signal by t naught, what will happen? It will be the same as x j omega multiplied by a phase factor. This phase factor is e to the power of j omega t naught. So there will not be change in the magnitude of the frequency spectrum, but in the phase minus omega t naught will be added. Conjugate property. If I have the Fourier transform of x of t x j omega, then if I conjugate means if the signal has a complex part, then the j part will be minus j, as you know. So this x conjugate of t will become x conjugate minus j omega. So there is a flip because of minus, and there is also a conjugate. This is called conjugate property. Time scaling property. If I have x of t, then x of at means scaling by a factor of a. Then when I change it to Fourier transform, it will be 1 over the absolute value of a times x j omega over a. For example, if a is -1, what will happen? If a is -1, x of t will become x minus t. So what is x minus t? Means the signal is flipped in time. So when you flip it in time, it will be flipped in frequency. We will get x minus j omega, and so on. Convolution property. Convolution property is very important. If I have an input to a system x of t, and the system h of t, the output is y of t is equal to h of t times convolved with x of t. The Fourier transform of this is y j omega is equal to x j omega times h j omega. You see, the convolution changes to multiplication, which is very important. So why it is useful? Because instead of, for example, getting the output by using convolution, we change h of t to h j omega, x of t to x j omega, and then we evaluate y j omega and change y j omega to y of t. Okay, let's go to the class notes. For example, here, convolution property, I have here h of t. Here, input is x of t, and system is h of t, y of t, x of t convolved with h of t, y j omega is x j omega times h j omega. To get yt, what should we do? We change x of t and h of t to x j omega and h j omega. That means to frequency domain. We determine y j omega, which is equal to x j omega times h j omega. And we convert y j omega to y of t using the inverse Fourier transform. Okay, this is very important property, convolution property. Okay, the other property is integration and derivative property. Okay, integration and derivative property. If we go to the slides here, this is again convolution property. the derivative of x of t by dt, dx of t by dt, when I change it to frequency domain, it will become j omega times x j omega. So if I have the first derivative of the signal, it will become j omega multiplied by x j omega. If I have the second derivative, it will become j omega square times x j omega. This is the derivative property, the differentiation property. Integration. What about integration? The integration from minus infinity to t x tau d tau, it will be 1 over j omega times x j omega plus pi x j omega at 0, the DC part of the value of the spectrum of the signal x of t, that's x j omega at omega 0 times Dirac omega. So there is this part, that means which comes from the DC. If the signal does not have a DC value, then this part will become 0. Okay? And then it will become 1 over j omega times x j omega. So if we see the examples in the notes again, let's say I have a signal g of t, Dirac t. What is this? The impulse signal. What is the Fourier transform? In the previous lecture, we found the Fourier transform of an impulse is 1. Okay? And of course, what is the unit step? The unit step signal is the integration of the impulse signal, Dirac tau d tau. Okay, let's call this Dirac tau is g of tau d tau. Okay? So the integration of, using the integration property, we have this. And what will be now the Fourier transform of the unit step? X j omega is equal to 1 over j omega times g j omega. G j omega means the Fourier transform of the impulse. That's pi g at 0, DC part, times Dirac omega. Because g j omega is equal to 1, the Fourier transform of the impulse, g at 0 will be also 1. So the Fourier transform of unit step function is 1 over j omega plus pi Dirac omega. We can get the Fourier transform of the impulse using the derivative property. We can just prove that again the Fourier transform of the impulse is 1 using the derivative property. And again, I use here the derivative property. Let's call u of t is x of t. So the derivative of u of t, which is x of t, is impulse. So using the derivative property, the derivative of x of t, the derivative of ut is the impulse. The Fourier transform is j omega times the derivative of the unit step, x j omega. Therefore, what is the derivative of unit step? We found it here using the integral property. So put here j omega times 1 over j omega plus pi Dirac omega. So j omega, cancel j omega 1, j omega times pi Dirac omega. Because Dirac omega is defined at omega 0. So omega is 0, this part will become 0. That means the final result is 1, which is Fourier transform of the impulse is 1. So this is the integral property and the derivative property. Impulse response of ideal low-pass filter. Okay, let's find the impulse response of an ideal low-pass filter. What is an ideal low-pass filter? As we studied earlier, the ideal low-pass filter passes low frequencies until omega c. Omega c is the cutoff frequency in radian per second, or Fc in hertz. So after omega c, it is completely 0. That's why it is an ideal low-pass filter. It is used as a benchmark for other filters. It is a reference, and it shows how good a low-pass filter compared to this reference filter, the ideal low-pass filter. Let's find the impulse response. That means we go from frequency domain to time domain. So h of t is 1 over 2 pi from minus infinity to infinity h j omega e to the power of j omega t d omega. We used here the inverse Fourier transform formula, okay? Because the signal is now h of t, and we should use h j omega. But h j omega is given from the graph. It is 1 between minus omega c and omega c, 0 everywhere else, okay? So we integrate from omega c to minus omega c, 1 e to the power j omega t d omega. Because we are integrating with respect to omega, then using the rule of integration, this will be 1 over jt e to the power j omega t. Evaluate from omega is equal to omega c. Omega is equal to minus omega c. We have e to the power of j omega ct minus e to the power of minus j omega ct. We can change this to sine because I have over 2j. It will be sine omega ct over pi t. And we can further change to a sinc function, omega c over pi, sinc of omega ct over pi. What is the DC value? The DC value of means the value of the low pass filter at omega is equal to 0. It is 1. Okay, the DC value is the average value. It is related to time domain by using this formula. Okay, if that means the DC value is omega equal to 0. So from Fourier transform, I have from minus infinity to infinity h of t e to the power of j omega t dt. So what should I do? I should replace omega is equal to 0. So this will be e to the power of 0. Therefore, the DC value h at 0 is from minus infinity to infinity h of t dt is equal to 1. So here, what is the point of bringing this example? We can find the DC value of a signal from the graph itself if the frequency spectrum of the signal is given. As you see from this, the low pass filter at 0 is 1. So its DC value is 1. The DC value means the average value of the signal integration from minus infinity to infinity h of t dt. What about the value of the impulse response at t equal to 0? The value of the impulse response at t equal to 0 also can be found from the inverse Fourier transform. This is 1 over 2 pi from minus infinity to infinity h j omega e to the power of j omega t d omega. Then at t equal to 0, e to the power of 0 is 1. We have this formula. The value of the signal at t equal to 0, any signal actually, at t equal to 0 is 1 over 2 pi, the integration of the frequency spectrum from minus infinity to infinity. For this case, h j omega d omega. So for our example, we integrate from omega c to minus omega c d omega. Then integration of d omega is omega. Evaluate from omega c to minus omega c. It will be finally 2 omega c over 2 pi, omega c over pi. This is the value of the signal at t equal to 0. We found it using the inverse Fourier transform. Because if I replace at t equal to 0 here, the result is sine 0 over 0. 0 over 0, again, it is undefined. We have to use L'Hopital rule. We differentiate with respect to time t, the numerator and the denominator. The numerator with respect to time, the derivative is this. The denominator with respect to time, derivative of pi t is pi. Evaluate at t equal to 0, omega c over pi, cosine 0, omega c over pi. And we can plot this sinc function, of course, it's very easy to plot this. And the zero crossing point, we can get sine omega c times t is equal to 0 is equal to plus or minus of n times pi. Pi is 180 degree, which we find it t is equal to plus or minus n pi over omega c. All right, now let's have an example of the convolution property. So as we said, for example, if I have a signal, input signal x of t and impulse response h of t, from chapter 2, how we find yt using convolution. But here we can use the convolution property. Y j omega is x j omega times h j omega. So we find x j omega, h j omega, we get y j omega, change it to time. Now, if you remember in the previous lecture, if I have a decaying exponential signal starting from 0, e to the power of at ut, the Fourier transform is 1 over a plus j omega. So what is e to the power of 2t ut? It will be, the Fourier transform will be 1 over 2 plus j omega, e to the power of minus t ut, 1 over 1 plus j omega. Then multiply the 2 y j omega, 1 over 1 plus j omega plus times 2 j omega. Okay, to find yt, we have this inverse formula, but in order to integrate this, this integration is a little bit complicated, not easy, but we can use partial fraction expansion. So we have 1 over 1 plus j omega plus 2 plus j omega equals a over 1 plus j omega b over 2 plus j omega. Then we find a and b, and after that we change it to time. So you see here, I relate it, I crisscross a times this, b times this. I have this. And then I group 2a plus j omega a plus b plus j omega b, and then rearrange to a plus b plus z. So the left equation equal to the right equation. Okay, that means 2a plus b is constant number. 2a plus b constant number is numerator 1. 2a plus b is 1. A plus b, I do not have j omega in the numerator part here. Therefore, a plus b is 0. So I have two equations, two unknowns. 2a plus b is equal to 1. A plus b is equal to 0. From the second, b equal to minus a. And then substitute in the first, I get a is equal to 1 and b equals to minus 1. Okay, this is simultaneous equation. Therefore, I found a and b. Change it to time domain. I use this property, e to the power of at ut for a greater than 0, 1 over a plus j omega, the Fourier transform 1 over. So the Fourier, the time domain, when I change this to time domain, this e to the power of minus t ut. When I change this to time domain, e to the power of minus 2t ut. So the overall signal is this one. Another property is multiplication property. Multiplication property, if I have two signals, x1t times x2t, okay, multiplication time domain is convolution in the frequency domain. It's 1 over 2 pi x1 j omega convolve with x2 j omega. Okay, this is very important property because we have in communication theory what we call amplitude modulation or modulation. Amplitude modulation is we have here an information signal S of t, and we have a carrier wave signal which carries the information, and here is multiplication of the two, the information signal times the carrier signal. I have a signal which is a transmitter signal R of t, S of t multiplied by P of t. So what happens if I see it in frequency domain? What will happen to the frequency spectrum R j omega? Okay, let's have this is the information signal. This information signal is we have a value between minus omega 1 and omega 1. After that it is 0. It's completely 0, and at omega 0 I have A. This is my information signal. Let me get the spectrum R j omega. Now R of t is S of t multiplied by P of t. R j omega, again using this property, multiplication property, it is convolution in frequency domain. 1 over 2 pi S j omega convolve with P j omega. P of t is cos omega naught t, the cosine, the carrier wave. Using Euler identity, it is half e to the power of j omega t plus half e to the power of minus j omega t. The Fourier transform of e to the j omega t is 2 pi Dirac omega minus omega naught, an impulse at omega naught. The Fourier transform of e2 minus j omega naught t is 2 pi Dirac omega plus omega naught. So I have two impulses, one at omega naught, one at minus omega naught, because I have 1 over 2 here. So the Fourier transform of p j omega is pi Dirac omega minus omega naught plus pi Dirac omega plus omega naught. Now, after this, therefore, we have this is p j omega graphically at minus omega naught and omega naught, two impulses. Now, r j omega 1 over 2 pi s j omega convolve with p j omega, s j omega convolve with this, s j omega convolve with Dirac omega minus omega naught plus s j omega convolve with Dirac omega plus omega naught, and pi will cancel pi. I have r j omega half s j omega minus omega naught, s j omega plus omega naught. So shift s j omega is shifted by omega naught to the right and by omega naught to the left. So I have the spectrum r j omega centered at minus omega naught and at omega naught. We call this modulation or modulation property. This is at the receiver. The receiver will do demodulation in order to retrieve or in order to get the original signal S j omega, the original spectrum S j omega. Okay, so another property also here I have very important property, total energy. In time domain, the energy of a signal is given by this formula, as you know, in chapter 1. We can get it in frequency domain also, 1 over 2 pi from minus infinity to infinity, x j omega squared d omega. So we integrate frequency spectrum from minus infinity to infinity divided by 2 pi. 1 over 2 pi, the absolute value of x j omega squared is called the energy spectral density. The multiplication property, we already talked about it. And you can go through this example. This example shows linearity and time shift property. And the derivative and the integration property also, we discussed it. Low pass filter, we discussed. And here, if I have two systems, H1T and H2T, what is the overall spectrum? Again, using convolution property, the overall impulse response is H1T convolved with H2T. In frequency domain, it will be H j omega equals to H1 j omega times H2 j omega. Okay, this is very important. This is the overall frequency spectrum of the signal. Okay, this exponential signal, I already showed this one. So the multiplication property also we discussed. That's all, students. I hope you understand this lecture, and please try to redo the examples by yourself to have more understanding. Thank you for listening to this lecture.